Good afternoon. My name is Jody Burnett. It's my privilege to serve as the current chair of the USU Board of Trustees. On behalf of President Noel Cockett, who is with us this afternoon at Utah State University, we welcome you to Research Landscapes, a new collaborative effort to provide evidence-based context, connections, and conversations on land, water, and air issues here in the state of Utah. We thank you for being here. At the outset, would you please join me in expressing our collective appreciation to Dave Peterson and O.C. Tanner for providing this beautiful space for us to meet. I also want to recognize our co-hosts for this event, that you'll be hearing from later, Teresa Foxley, the President and CEO of the Economic Development Corporation of Utah, and Alan Matheson, the Executive Director of the Utah Department of Environmental Quality. Thank you both for sharing this event with us. At the time that you RSVP'd for this event, we asked you to provide some feedback on a few questions. And at the outset, I'd like to share just a few of those results with you. 80% of you believe that air quality is among the three most important issues facing our state right now. Almost 90% of you believe it will take significant effort to create meaningful improvement in Utah's air quality. Nearly all of you believe the job of improving air quality belongs to all of us as citizens, business leaders, state and local government. Having said that, however, only 64% of you listed air quality monitoring and data collection as one of the initiatives you think is a good idea to improve air quality. We're hoping that today we can change that perception and show you a little bit about some critical lessons we've learned by research and observing air quality trends along the Wasatch Front and throughout the state. Our goal for the next hour or so is to share with you just a glimpse of the critical research being conducted by Utah State University in the area of air quality. Remember, it's just the tip of the proverbial iceberg, and I hope you'll treat this as a starting point for understanding what types of resources we can provide as we all work together to solve the problems and challenges our state is facing. For the remainder of our time, we'll initially hear a few remarks from three speakers, and I'm going to introduce them all at once in order to not interrupt the program. Our first will be Teresa Foxley, as I mentioned, the President and CEO of the Economic Development Corporation of Utah. Prior to that position, Teresa was a senior leader in the Governor's Office of Economic Development. Then we'll hear from Randy Martin, one of the state's leading experts on fine particulate pollution in Utah. Dr. Martin is a research associate professor of environmental engineering at Utah State University with a joint appointment at the Utah Water Research Laboratory. He has been at USU since the summer of 2000, combining research, teaching, and outreach duties associated with all things air quality. He also serves as an associate director of the Utah Climate Center, where his duties are associated with maintaining the network and monitoring sites. Dr. Martin has also been a member of the state of Utah's Air Quality Board since 2017. His research interests center around the characterization and behavior of ambient fine particulate matter, reactive hydrocarbons, and related oxidation products such as ozone. I'm surprised I got through that, and I'm sure Dr. Martin will enlighten me as to what that actually means. He's been heavily involved with studies of the Uinta Basin's wintertime ozone issues, fine particulate matter in the Cache Valley and along the Wasatch Front, and mobile source emissions related to Utah's vehicle fleet and regional conditions. He will frame and discuss research findings that he thinks are critical for Utah, and will also highlight some of the statewide research partnerships that we have. Finally, Alan Matheson will talk about steps the state is already taking to improve Utah's air quality. As I mentioned, Alan is the current director of the Utah Department of Environmental Quality. Prior to that, he served as an environmental advisor to Governor Herbert. We hope you'll have questions for our speakers, but in the interest of time, to make sure we cover all of the agenda and to complete our program respecting your time, we'd like to ask you to save them to the end. So let's start by having you join me in welcoming Teresa Foxley, our first speaker.
Well, thank you, Jody, so much for the warm introduction, and I'm absolutely delighted to be here today. Thank you, President Cockett, for organizing these fantastic events, and it's great to see so many friends and partners in the audience. For those of you who don't know me or who don't know EDC, let me give you just a quick background about why our organization cares about air quality. So EDC Utah was founded by providing economic research, marketing, and corporate recruitment project management on behalf of companies who are considering Utah as a potential site for a location for their operations. So in doing this, we tend to have about 110 projects on our books at any given time, or companies who are actively considering an expansion opportunity in Utah. And most of those companies are simultaneously considering other states as part of their search or as part of their efforts. And so people naturally assume, well gosh, air quality must come up in your day-to-day activities as you're interfacing with these companies on their site selection criteria. And people are oftentimes actually pretty surprised to find out that in our day-to-day, air quality is not a big issue in corporate recruitment. What is really driving corporate recruitment today is talent acquisition. So talent acquisition, talent cost, talent availability, those are 3 of the top 5 site selection criteria. So why do I care about air quality so much if what I'm telling you is on a day-to-day basis, air quality doesn't come up in our site selection conversations with companies? And it really is that tough. So we found in partnership with Envision Utah, as we worked on our point of the mountain development process, that the #1 reason why individuals would relocate outside of the state of Utah is actually because of our air quality. I thought this was really interesting because we talk a lot about in the state how there are items that we'd like to improve. We talk about wanting to improve educational outcomes and other things, but really we found that through that research that talent is incredibly concerned about that issue. It's also something that we found in our internal polling with stakeholders. So we do a lot of data gathering amongst the cities, the counties, the private businesses, and the organizations that we work with throughout the state. And those companies, those who will really drive a lot of the economic growth in this state, are firms that already exist in the state of Utah. And they are telling us that this is an issue for them because as they think about bringing in highly skilled individuals from outside of the state, again, it's not some of the issues that you would typically think that are an impediment to somebody relocating, but it's air quality. And so I, again, appreciate the Utah State University for planning this and for letting us be a part of the conversation. If Utah is to remain competitive, it means we need to retain and attract the most highly qualified individuals that we can in the state. And so to me, this air quality issue is one of utmost importance and one that I appreciate the university for having such attention on this matter, and look forward to working with you to be a part of the solution. So thank you.
Well, great. As was said, my name is Randy Martin. I'm on faculty up at Utah State, and I have been doing air quality research for a long, long time. And I hope to tell you a little bit about it. This is how I wanted to dress to come here. How you're going to see me if you ever bunch of me out in the field. I couldn't make myself wear a tie today, but at least I wore the team shirt. At least to be somewhat presentable. So first I want to tell you who I am and why I'm an environmental engineer. I'm going to probably step up here so I can point out that, maybe I can point out. I'll show it there. Okay, there it is. I grew up in the great state of Montana. And I'll tell you right now, Montanans are probably the only other people besides Texans that are really arrogant about their state. So everything I'm going to tell you about Montana is going to be great, except for one thing, and that's why I became an environmental engineer. When I was a kid, probably 10, 11, 12 years old, my brother and I used to go fishing all the time. My parents, God bless their souls, would drop us off and come back and get us 4 or 5 hours later, and we'd go exploring. And we were hiking up in the Little Belt Mountains in Montana, and my brother and I, we went off to a tributary stream, and we noticed the stream was crystal clear, and it was full of all sorts of pretty colors on the rocks, golds, blues, yellows, reds. We thought, oh, this is cool, this is really pretty. There were absolutely no fish in that stream. When we got back, I started talking to some people. I said, yeah, what's going on with this stream up here by Monarch? And they said, oh, that's acid mine drainage. That's coming off the gold mine that was up there back in the 1800s, and it's polluting that stream. It's killing the fish in that stream. And so at that point, I knew I wanted to get into something environmental. I didn't know exactly what. You know, when you're 10, 12 years old, you want to be a forest ranger or something like that. But by the time I was 16, I knew I wanted to be an environmental engineer. And so I ended up going to school in Butte, Montana, at Montana School of Mines. It had one of the first environmental engineering accredited programs in the country. I think we're were number 6 at the time. And when I graduated in 1982, I had my choice. I could go live in Lander, Wyoming, which I'm Montana, boy, that'd be okay. But I also had a job offer in Birmingham, Alabama. And I thought, what the heck? I'm going to be adventuresome. I've never lived in the Southeast. I love barbecue. I'm going to go there. So I went there, and I worked there for 5 years for a research company. And I got to actually participate in active research on particle and gaseous control technologies, baghouses, scrubbers, ESPs. I got to really do a lot of research in particle control measurement, particle sizing measurement, which was really exciting for a 21-year-old kid. I got to write EPA regulations at the time. I got to publish papers, and I thought, this is what I want to do for a living. But I reached a point in my career where I couldn't go any higher with that company. So I said, time for graduate school. But before I left Alabama, I married my girlfriend, and we moved off to Washington State, where we went to Washington State University. Washington State University, I will tell you the same thing I tell all my colleagues at Weber State, this is the real WSU. It's just like I tell my colleagues at BYU, these are also the real Cougars. I was there for 5 years where I got my PhD and my master's, and I worked on a lot of ozone photochemistry and hydrocarbon species, particularly called biogenic hydrocarbons. They're just as reactive as the hydrocarbons that come out of the tailpipe of your car, but they come from the biosphere. So if there's a lot of those around, you have to know about that. When I graduated there in '92, I moved to Socorro, New Mexico, and went to work for the Mexico School of Mines as an environmental engineer doing air quality. Once again, a lot of ozone research, now it's ozone in the Southwest, as well as a lot of particle or long-range transport research, as well as a lot of fire-related research. We had a lot of fires down there, so it's kind of coincidence that I was able to study that. In the year 2000, my wife and I, we started having kids. I had some family that was living in Salt Lake at the time. I thought it'd be kind of nice someday if our kids could grow up near their aunts and uncles. Utah State happened to have a job opening. I thought, well, I'll apply. And they offered me money and said, come on up. And when I came up, I fell into this wonderful laboratory of the Cache Valley. I had no idea that we had high exceeds of PM2.5. They didn't know. We actually started measuring it there in 2000. And so it was a great laboratory that I fell into, and I've been doing small particle research since then, summer, wintertime ozone, and a lot of that has led me to become, I hate to admit this because it sounds really arrogant, but probably the ammonia expert in the Northwest, particularly from agriculture. I've been doing a lot of that in the last few years. So that's how I got to be where I am. And my research here at USU, I was thinking about this, and it actually goes in with what Jody Burnett said about measurements and why we do what we do. And really, it's so we know which knobs to turn. I want to know how to control the air pollution that's out there. So that's what I like to do. And so I like to look at these things. Is it transported in from a long way? In other words, is it not our fault? Is it from point sources, large industrial facilities? Are there area sources, which are small businesses, agriculture, landfills, residential sources? Or is it mobile sources, passenger cars, commercial vehicles, mass transit, planes and trains? Those are all of our potential sources. This is why you've got to go out and make measurements to know which of these knobs to turn. So I'm going to tell you a little bit about some of the work that we do. I'm going to tell you a little bit about some of the work we did in the Uinta Basin ozone issues. I'm going to tell you about some of our mobile source emission measurements. And I'm going to tell you about this new study we're doing right now, looking at ammonia and chloride here in the Wasatch Front. So let's talk about the Uinta Basin ozone first. First, you got to understand a little bit about what ozone is. Ozone is not emitted from anything. Ozone is formed from volatile organic carbons, also known as hydrocarbons. It's formed from oxides of nitrogen, which is produced anytime you burn anything with air. It's going to produce oxides of nitrogen. The other third key ingredient is sunlight. You have sunlight, you have those two chemical species that we call precursors, and then you're going to form ozone and other products. And those other products can cycle back in and form more ozone. So you've got to understand all that. When you look at those three components there, first thing to think about is typically ozone is formed in the atmosphere. It's not emitted from anywhere. It's a summertime pollutant because it takes sunlight. So if you have a lot of sunlight, then you can have ozone. And so you associate it with large metro areas. And typically if you hear about ozone, you think of Los Angeles, Houston, maybe Washington, D.C., Baltimore. Well, in 2005, in the Upper Green River Basin in Wyoming, they had a couple of ozone monitors sit out there year-round. And in the winter, they spiked up to above the standard. And everybody thought, what the hell's going on? Our instruments, I sit in a meeting here in Salt Lake, and they're saying, our instruments are bad. You can't have two instruments at fail at the same time? Well, maybe we had long-range transport. Well, no, because you were inverted and there's no way air could mix in. So they started thinking about what was really going on. And they did lots of studies, and what it came down to is high elevation, which means you're closer to the sun, just like you get sunburned when you go skiing, right? Snow cover, which bounces that sunlight back, so it essentially doubles how many photons are available. Low inversion height, so you're trapping that air that's there in the basin. Light horizontal winds, so you get a little bit of mixing. And then the big thing is abundant precursors. And in the Pinedale anticline, oil and gas development was going through a big boom at that point. So they had lots of potential to form ozone, and they did indeed form ozone. So as good researchers, what's the question you ask yourself? Anybody know where that picture is? See you into basin. What do you have when you went to basin? High elevation, snow cover in the wintertime, low inversion heights, light horizontal winds, and abundant oil and gas development. So what happened? Well, in 2009, a cooperative agreement between the EPA, some of the oil and gas folks, as well as the Ute Indian tribe, set out a couple of monitors. Actually, there were 4, I think. And there's one at the National Monument, too. And they saw exceedances. So that got the state's attention, DAQ. They said, let's go out and do a study. So I went out, or we set up a whole series of studies, 2010 and 11, 2011, 12, 13, 14. The first study was a very preliminary study. It basically involved Utah State, the Energy Dynamics Lab, which is now called the Space Dynamics Lab. This is what that study looked like. We went out there, and all the red dots were the existing ozone monitors. We put out the yellow monitors for the winter of 2010, 2011. All the green little dots, those are the active oil and gas wells at the time. Black dots are what we call the small point sources, compressor stations, and those kind of things. So there's abundant potential out there. And just to show you how much fun we have, this is one of our sites. This was at Fruitland, and we actually would have to go dig it out because it snowed so much that winter. And on that day, it was actually minus 18 degrees, and the wind was blowing at least 20 miles an hour. So we are a dedicated bunch of people that go out and dig this. And one of Wyatt, wherever he is, he said, "Is that a grown adult?" I said, "Yeah, grown adult in that picture." So, what did we see that first winter? Well, this is what we saw. Don't get too caught up in the numbers, but the thing to point out is we saw lots of different times where the ozone level at all the sites was well above the standard, double the standard. So there was a huge problem. And you can also see that it's very episodic. 1, 2, 3, 4, 5, 6 or so episodes. And those all charted with inverters, just like we see here in the Wasatch Front. If you count all that overall, according to EPA regulations, you're allowed to exceed the standard 4 times. Actually, you're regulated at your 4th level. This is how many times they exceeded in the Uinta Basin. The red lines on the perimeter of that figure is 4. And as you work your way into the basin, you can see that they exceeded it actually up to 25 times at Ouray there. So as you went into the center of the basin, huge amounts of ozone. So that was real interesting. We're seeing it. It's happened. It's a big study. That got a lot of interest from the national researchers. For an investment of about $200,000 from the Division of Air Quality, EPA, NOAA, NCAR, lots of other universities contributed to the next study, which we call the Uinta Basin Winter Ozone Study. If you want to look it up, you can find it on the DAQ webpage. But a huge multi-agency study, lots of investigators, everybody was willing to go. Plus, we also established at the time an air quality research group at the Bingham Center at USU Vernon. So we got some really on the ground. We were all geared up, we all got out there to go, and large investment, no winter. That's what happened when you do environmental work a lot of, not a lot, but sometimes. And if you looked at it, we didn't have any exceedances. So we couldn't study the photochemistry we wanted to study. Although we could study lots of other things. We did lots of measurements of the hydrocarbons, the NOx. We looked to see where they were coming from. Just to give you an idea, this is one of the graphs that everybody thought was really cool. We generated it. And what this shows you is the ratio of reactive hydrocarbons to methane. Methane's on the x-axis, reactive hydrocarbons on the y-axis. And when you look at that, these data were all taken at one place called Horse Pool. If you look at that, what do you see? Well, what you see is 2 regimes. It's got a slope right there and a slope right there. more vertical one here, and then a horizontal one. And if you look at the little colored dots, it's when the wind direction changed that those ratio changes. And that tells us that there's different types of sources out there. Specifically what we found from these type data is that the oil wells put up different gases than the gas wells. And they're all equally reactive, or they're all importantly reactive, but there are different amounts at each level, so we gotta go out and know that. And that's the kind of thing we found in this year. Well, 2013, 2014, we had UWAS Light. Instead of a $3.5 million study, it was like a $1.82 million study. And yay, we had a winter. We actually had lots of exceedances once again, so we got to do a lot of very interesting work, and I won't bore you with all the explicit details, but I do want to show you one thing, just to brag on us a little bit, is we took out one of USU's Aggie Air UAVs. See, oops, no, there it is, good enough. Go back to that one. We miniaturized an ozone monitor, and we set it inside the payload of the UAV. And we took it out there and flew it around. So this is how you launch it. You can barely see a little string right there. This is how we launched it at the time anyway. It's a giant rubber band that's hooked to the ground. You can't really see it over there, right there. So you stretch it out and let it go, and then hopefully you swoop up and fly away, and then you can fly it around and map the ozone. Well, as you already saw from the first graph, it didn't always swoop up. Fortunately, we were in snow, so it wasn't too bad. What we got was some really cool data that looked like this. And what this graph shows you is what I call a vertical curtain of ozone. And what it shows you is the ozone is highly concentrated near the ground. Once you get above what is the inversion layer, about 400 meters, it's background ozone. So everything's being reacted and formed near the ground, which tells you that it's a very localized source. So we know it's being created in the Bingham Basin. We've got lots of data like this. I encourage you, if you're interested, to look up the final reports. It goes into much, much more detail. Following that study and beyond, Dr. Seth Lyman out at USU Vernal has established a great continuing research program out there where they're kind of fine-tuning what we know.
We're really at the north end of the area of the Uinta Basin with the most dense oil and gas industry development. I'm Seth Lyman. I'm a research associate professor in chemistry at Utah State University and also direct the Bingham Research Center. The larger trailer here is our main trailer at this station, and inside we measure ozone, we measure oxides of nitrogen, organic compounds in the air. We have a gas chromatograph to measure methane and non-methane hydrocarbons. We measure particulate matter in the air, that's the haze you can see. These kind of silvery cans actually collect whole air samples, and we bring them here and they open and fill slowly and just fill with air, and we take them back into the laboratory to measure individual hydrocarbons like ethane, propane, butane, benzene, things like that. Organic compounds come out of your car's tailpipe. The percent that's this or that compound is really different from what comes out of a natural gas leak at a well pad. To get down to that level for these compounds, you really need kind of a big, complicated machine. That side is a gas chromatograph, so that separates each compound out, and then we analyze them by mass with a mass spectrometer. The people who work in the oil and gas industry are our friends and neighbors. They also care about air pollution and health and things like that. The key, and really our group's mission, is to do research that helps industry and regulators make good decisions.
Seth out there is really focusing on the hydrocarbon side of things, because it turns out hydrocarbons, particularly a species you probably all heard called formaldehyde, it is both directly emitted from some sources out there, but it's also formed in the atmosphere from other hydrocarbons. And Seth is trying to narrow those down, because formaldehyde is extremely reactive and it forms a lot of the radical species that go on and form ozone. It's a really complex chemistry, but Seth and his crew out there have done a really good job of not only measuring, but also they're developing models that are working very specifically and very nicely for the Uinta Basin. Just about to tell you all about the car stuff.
Isn't this what Ari did about 60 years ago?
In Caltech at the Los Angeles Basin? Yeah. Yep, except that was summertime also. But it's the same basic reaction.
Right.
Yeah. Photochemical. We just got to understand where those precursor hydrocarbons and also whether it's the hydrocarbons or the NOx that are the limiting reagents. Out there, they're hydrocarbon rich. And so we need to know which of those hydrocarbons are the most important one in order to get pest control. I've got a really good picture I'm not going to show you can't remember what I was going to say. A really good picture of what? Got a lot of good pictures, actually. Oh, you go. I'm good with this one. So we're done with Seth. All right, so Seth, like I say, has done a lot of great work out there, and they continue to do a lot of good work. If you have specific questions about the basin, contact Seth. I'd be happy to. Oh, I know what I was going to say. Seth has also developed a web page where you can look on it. It's ubair.usu.edu, where you can look and see what the ozone is out in Uinta Basin right now. And this morning, it started going through the roof. If this storm front makes it out there, they'll clear out. But right now, they were already exceeding at 3 or 4 stations. Okay, we're back to car emissions, mobile sources. Mobile sources are an extremely important part of our what we call our emissions inventory. The Wasatch Front emissions inventory, this is from the DAQ, estimates that about 48% of all direct emitted pollutants come from the mobile sources. So that's all of our cars, our trucks, our trains, planes, all of that counts as mobile sources. So we want to understand what are the particulars, what are the worst types, what are the best types. We've done lots of work, we're still doing work on mobile sources. In 2004, we did our first on-road study. I'll tell you a little bit about that one. In 2007 and in 2011, we compared buses to cars. Is mass transit really a good thing or not? I'll tell you. In 2013, we did a study on cold start versus hot start versus idles. I'll tell you about that. We've also done an on-road study of driver characteristics. We looked at old drivers, young drivers. By old and young, I mean haven't been driving for less than 5 years or more than 10, and then male and female. I'm not going to share that data with you because it's kind of long and diluted, but which group of those do you think had the lowest emissions? By a long shot.
Women.
It was young female drivers. They had the smallest variation and the lowest emissions. We were all, I won't say stunned, but surprised. We thought the older experienced drivers would be more consistent. We did an on-road study a couple years ago about is the pollution inside your cabs better than the air outside? And we're doing studies right now, we're just gearing up, looking at how much ammonia, there's my ammonia, how much ammonia is coming out of the tailpipe of your cars as well as big diesel vehicles. So I'm going to tell you about these first 3 real quick. In 2004, we borrowed a van from Utah County. They had a van at the time that had a laser-based system. That little box you see right there, right here, shoots a laser across the road, bounces it off a retroreflector. When the car drives through, we can tell how much of that laser energy was absorbed by specific gases. So, when we did this measurement, we did it in the Cache Valley, we did it on highways, we did it on surface streets, we did it on uphills and downhills, so we wanted to get all sorts of different driving conditions. We ended up counting about 12,000 vehicles. We had an average vehicle speed of about 34 miles per hour, so we got a good cross-section. And we ended up with results that showed us that for oxides of nitrogen, one of the key components, and for VOCs, we found pretty much what everybody else in the world found. So our vehicle fleet wasn't different. And that thing was 5% of the vehicle fleet would fail an emissions test for NOx. That 5% was responsible for 25% of the total NOx emissions. For VOCs, the picture was even grimmer. 10% would fail an emissions inspection program, and they were responsible for almost 50% of all the vehicle fleet's emissions. So those are what we call gross emitters. And the only way to clean up that huge portion is to have an I&M program, a inspection maintenance program. Took Cache Valley a little while to put one in place, so that was in 2004. 2014, we finally got an inspection program in place. And our failure rate for those first 2 years was 8 to 12%, almost exactly what we measured. So the one statistic that was quoted, 64%, only believe we need measurement programs and monitoring. This tells you why we need to do it. The other study we did was looking at mass transit. And the way we approached this was, how many drivers would we need to convince to park their cars and ride the bus in order to see a net increase in the air quality or a decrease in your emissions. So what we did is we measured the tailpipe emissions of buses. We put students on the buses, or I rode the buses. We rode buses several different days, several different routes. We made measurements of CO, NOx, CO2, and hydrocarbons. Then we measured cars so we could compare them. And what we found in 2007, now this is a little bit hard to look at the first time, but for NOx. So for NOx, you would have to get 27 drivers or 21 drivers to get on a diesel bus in order to see a net decrease. So you have to fill the bus up. For a natural gas bus, you had to put 48 drivers on there. Not real practical. Hydrocarbon was a little bit better picture. One driver would get on a diesel bus and you'd see a net increase in emissions, or decrease in emissions. Carbon monoxide was a little bit of a mixed picture. And then in 2011, we had the opportunity, mainly because I had a really, really motivated student, and he wanted to do this study. And the bus fleets had turned around, they modernized their bus fleets. So we did the study again, and it was remarkable. You put one driver, former driver, on the bus, and you see a net decrease in the emissions into the airshed. So this legislation that's going through right now, looking at funding mass transit, here's a reason to do it right here. I saw driving in today, billboards over the highway. Thursday and Friday are fare-free days. Take advantage of it. Make a big deal about it. Call the press and say, hey, I'm riding the bus, I'm saving air. Because you will be doing that. The cold start, hot start. Anna and I kind of argued about this picture because I wanted to use it. This is how we did tailpipe measurements. This particular truck, they had actually cut out the catalytic converter. So this was one of our real gross emitters. That's part of the study. There is a population in our vehicle fleet that does that. But what we wanted to do was measure vehicle fleet in northern Utah and see whether a cold start, when the vehicle's been off for 12 hours, how much emission you have across all the vehicles representative of northern Utah. We did a hot start, which means you drive the car around, shut it off, and start it again to see how much emissions are going on. And then compare that to idle. So, first thing I want to point out is a little survey I had my students do. How many people idle? So I just told them, go sit out by a bank, go sit out by a convenience store, count them. At banks, about 14% of the people were idling. This was in December in the Cache Valley. Convenience store, 21%. Shortly after we did this study, the first vehicle was stolen in Cache Valley at a convenience store. It was left running. It was a donut delivery truck, too. Elementary schools, where kids drop off, or the parents drop off, or banks pick up their kids, 46%. And then USU, Center of Higher Learning. What do you think, President Hackett? 63%. Not real happy about that one, yeah.
Every university has their niche, their expertise. And Weber State has always reached out to Randy Martin, who represents Utah State Universities. And due to this collaboration, we have come up with our cold start research. So we had close to about 70 to 90 vehicles that was a kind of a reflection of the vehicles you find in the street. We put the vehicles on a dyne, and then we were measuring the emissions coming out when the car is cold, while it's hot, and then while it's driving down the road. And then we can plot out and see, all right, when the car was cold, the catalytic converter didn't work. So the emissions were high. And then when the catalytic converter got heated up, warmed up, the emissions dropped. So we knew then we have a cold event in every start. There's so many clean cars with clean technology, but there's a lot of them. And so they're still a major contributor to our air pollution problem. The work Utah State and Weber State did together is to educate drivers. Look, there is responsibility you must take as an owner of a vehicle, because every time you turn the key on, you're making an action that produces emissions.
That's Joe Thomas. He's on the faculty at Weber State in what's called the NCAS group, National Center for Automotive Science and Technology, and we collaborate on a lot of work in his shop, and we do it at the Water Lab at USU as well. So getting back to what we're talking about, this hot start, cold start, idle. question that we wanted to answer was, how long does my engine need to warm up after a cold start before the pollution is minimized? This is not until the cab is warm, but until the pollution is minimized. So we measured all these cars. The average data, boom. That peak actually occurs at 12 seconds. At 12 seconds, all your emissions are declining because your catalytic converter is heating. So, what you ask yourself, how long should I warm up my car? Really no more than 12 seconds. What I tell my kids, scrape your windows and drive away. You don't have to wait for it to be warm inside. You have coats and gloves for that. So you can drive away. So what I tell is, general rule of thumb, 1 to 3 minutes and you're good to go. And in fact, if you just get in and start it and drive, your catalytic converter is going to heat even faster, and that curve is going to be a lot lower. And if you add up all those cars that Joe was telling you about 75% of all your emissions occur during that cold start period. So if you can minimize that, you're going to minimize the amount of pollutants into our local air. Okay, should you let your car idle when you go in for a short stop? You're dropping or picking up people at USU. Intuitively, no, right? But we needed data to prove that. So what we did is we took cars, drove them around, shut them off, let them sit for 5 minutes, let them sit for 10 minutes, let them sit for 20 minutes, and then restarted them. And those are what your total emissions look like. They increase a little bit as the time the engine sits warm but off as you go out 20 minutes. But then if you look at how much you're emitting when you idle, boom, significantly more. So the rule of thumb that we tell people, I think it's actually on the next slide, if you put your car in park, turn the engine off. That's that simple. If you do that for 5 minutes, as a hot start compared to an idle, 4 times more VOCs for an idle. 3 times more NOx. NOx is a function of engine load, so when it's idling, it's not really under load. But 10 times more carbon monoxide. So it's a huge, huge issue. And carbon monoxide is the one that you're going to notice most as a human being. So when you're out there waiting, picking up your kids, think what you're doing to the poor little crossing guard there. She is breathing all that carbon monoxide. So yeah, turn your engine off. The other thing I want to talk about is this Wasatch Front ammonium chloride work that we're doing. And to set that up, I need to set up a little bit about the pollution, the PM2.5 pollution in the Wasatch. And by Wasatch, I also mean the Cache Valley, for example. And if you look at that, look at the particle composition, the PM2.5 chemical composition. The biggest slices of our pie are ammonium and nitrate. And that's actually one species called ammonium nitrate. And I can't speak quite as much for Cache Valley and Utah Valley. I can tell you, for Utah Valley and Salt Lake, for Cache Valley, when our particles get above the standard, instead of just about 70% or 80%, it can get up to 90%, 95% of the total mass being ammonium nitrate. So if we want to control our particle mass, we need to know where the ammonium nitrate is coming from and which side of that, the nitrate or the ammonium, is the dominant reaction. Which knob are we going to turn? There are also, I'll point out, the dark gray and the light gray, the organic compounds, those could include wood smoke. Fireplaces. Fireplaces tend to be more locally important, neighborhood important. But the other part of that other could include ammonium chloride. We live near the Great Salt Lake, lots of potential chloride out there. So we wanted to find out what the effect of that is as well. So there's been a series of studies. We all working through a series of studies. And the first major study was in 2016, and I call this a bootstrap study. It was basically a couple of researchers from DAQ and a few other researchers from USU and Weber and Utah. We were curious. We wanted to do a study, so we basically put our own money into it. We did it kind of on the cheap. We borrowed some equipment from NOAA, and we did this study, and we found enough interesting stuff that we convinced other agencies to come in 2017. And that was the Utah Winter Fine Particulate Study. And again, that study is available at the DAQ webpage. That was I might get the number wrong, I think it was about a $2 million study, and the DAQ had to put up $130,000. So it was a great, again, we started something, other people understood, and they came and did this study. And this study was really cool because it was from Provo to Logan. We did aircraft flights, we did balloon flights, we had outfitted automobiles we drove around and measured, and we had 6 stationary sites, 2 in each of the main valleys, looking at all this air pollution. And then in 2019, what we call WAFACO. I'm not really good at coming up with acronyms, so that's what we ended up with. It stands for Wasatch Front Ammonia and Chloride Observations. This is, again, a Logan to Provo study, and it was very focused. I'll tell you a little bit about that. The first study, 2015-2016, what we found was 2 main things. One, that there's a different chemistry of particle formation at night and during the day. Both are nitrate dominated, but through different pathways. And so, where do you go to control it? We don't know, we just know it's different. And then we also found ammonia all throughout the Wasatch Front, much, much higher than the emissions inventory suggested. Where is it coming from? In the Cache Valley, we can figure it out. We're ag dominated up there. So we can figure that out. Here we don't know. So, the Utah Winter Fine Particulate Study, I won't go through these in detail, but these were kind of the questions we were asking. Are there spatial differences, not only within the valleys, but inter and intra-valley differences in the PM2.5 and the key gases? Do they vary at time of day? How does the Great Salt Lake and Utah Lake affect the particle formation and the meteorology? Are there other significant sources of aerosols, wood smoke, ammonium chloride? What are the sectors that are important? So, very quick, we're going to rip through this very quickly. We were able to capture inversions. And so each of those bars on the top of the graph shows you what we call our intensive periods, where we actually saw inversions set up. And then towards the end of that, you can see we had high levels of pollution, PM2.5, and yay, Cache Valley was the worst that year. I say yay, I get all excited, there's something for me to study, but it's affecting my health too. So it's not a good thing, but from the science, it's a good thing. So we have things to study, we successfully studied it, and we had lots of key findings. Let's go through these real quick. Folks at the University of Utah and NOAA were able to capture and model the inversions fairly well, meteorologically. They did a really good job, and they're still doing a good job. The PM2.5 distribution was fairly uniform across the basins. That's what's kind of interesting. If you notice on that previous graph, Provo County, Linden was almost the same as Hawthorne here in downtown Salt Lake. Hawthorne's just right over here, the measuring site. So very similar PM2.5 concentration. Once again, ammonium nitrate was the dominant species. The NOx, the nitrate side of things, it was more distributed than the PM2.5 itself, but it was really well predicted by the DAQ emissions inventory. Again, both daytime and nighttime formation pathways are important. And again, we saw an abundance of ammonia. We still don't know where it's coming from. And then this is kind of the key thing. Which of the ammonium nitrate reactions are limited? Do you control the ammonia? Do you control the nitrate? So this graph takes a little bit of explaining, but what you see here are 2 different inversion events and a set of dotted lines, Cache Valley, Salt Lake Valley, Utah Valley. So if the data points are below the line, that tells me that we are in an ammonia, in an ammonia-rich or nitric acid-limited regime. And if it's above the line, we're an ammonia-limited regime, and or ammonia. Really should say ammonia-rich. They're backwards. Sorry, Anna. Top line is ammonia-rich. Bottom line is nitric acid-rich. So, what do you see in the Cache Valley? Everything's below the line. We're ammonia-rich, and we know that. We've done lots of measurements. We know more about the ammonia up there by a long ways. Lots of measurements. We're ammonia-rich in the Cache Valley, so it doesn't pay us anything to try to control ammonia in the Cache Valley. If you look at the Salt Lake Valley, sometimes we're ammonia-rich, sometimes we're nitrate-rich. And it depends on which phase of the inversion you're in. At the start, we're ammonia-rich. In the middle, towards the end, we're nitrate-rich. So different things are going on at different times. So down here, we have to control them both. That gets us back to that, which knob do we turn? So this year what we decided to do was really focus on trying to understand the ammonia, and since we're doing ammonia, it wasn't that hard to do chloride, so we're going to do chloride. So what we did, we set up 40 sample stations from Brigham City all the way down to Mona. And I've got colleagues from the University of Utah, from BYU, that they're sending all their undergraduate students that are running out there every Saturday swapping out our samples, and we're analyzing all of them at Utah State. We've also got particle samplers that we set out at 10 different stations all around so we can get particle characteristics. And then we also have a real-time ammonia monitor that collects data every 1.5 seconds. And we bounce around from specific sites looking for kind of hotspots, like we had it near the highway, we had it near Rose Park, we had it out of Camp Williams, so we could see if there's any interchange between Utah and Salt Lake Valley. And then we also were fortunate to have the EPA come out and join us with their mobile van, so we could drive around and look for hotspots. And so I'm just gonna, first of all, I see that I got one more video.
Ammonia plays an important role in driving our high particulate levels that we see during the winter. But while we know that ammonia plays an important role, we don't know where it's coming from. This is Bonneville Station. It's one of DEQ's several air monitoring stations, and this station is strategically located to monitor air pollution levels that could be coming from the several industries that are located in this area. So researching air quality in Utah is quite fun, and the reason for that is that it's a really complicated problem. We have these sensors deployed at 40 different locations. I actually have the same sensors running in my backyard. This is for measuring ammonia, and this is for measuring hydrochloric acid. So with these samplers, we only get 7-day averages of data. I've arranged to get EPA involved in this project. So EPA, they have a mobile air monitoring truck that they're gonna be bringing here to take real-time measurements. Once we identify where ammonia is coming from, then we can come up with controlled regulations to target those sources that mostly contribute to ammonia. We can use that information to inform policy.
Like her, my wife's chagrin, my backyard is an experimental station for whatever we have to be. As is my inside of my house. So this is data literally hot off the presses. I generated this graph last Thursday night. And what this shows you is the hydrochloric acid we measured at those 40 sites. And so this is, you are the first audience to see this besides about 5 of us researchers. What do you see? First of all, the numbers are very similar to a summer study we did, so I believe our data. But where is the hydrochloric acid concentrated? It's on the west side. I'm not going to say too much about where I think it's coming from at this point, because this is just one graph. I've got 3 more weeks of data that I've got to go through. But it's interesting, and I think it points to some potential sources. Here is the ammonia graph hot off the presses, also generated last Thursday night. And what do you see? Well, generally, first the concentrations are all pretty reasonable on average. But generally up north, not too high concentrations. There is a big bullseye here in the Salt Lake Valley. Any guesses? It's a landfill, West Jordan landfill. And then mostly though, the higher concentrations are down in Utah County. So there is the potential that ammonia from in Salt Lake could be blowing up from Utah County. We don't know that yet, but some of our data will point to that, hopefully when we get done reducing it all. This slide shows you one of those drive-arounds in the EPA van. This happens to be in the Salt Lake Valley, and surprise, surprise, it's by a landfill. If you remember the concentration from the previous graph, it was around 10 parts per billion. And when we drove by the landfill, you can see that it started out low and then ramped on up to about 110 parts per billion. The picture was from Google Earth, so it's a summer picture. We actually did it in wintertime a few weeks ago. More dramatic. This was up in the northern Wasatch. And we were driving along, got a much higher peak, 900 parts per billion, near a dairy. Not surprising. I didn't happen to know a dairy was there until we drove by. Oh, look. That's not the highest we saw. We were down in Utah County. And this one's a little hard to see because the scale is larger. But we were driving by a field, and they had obviously just land-applied fertilizer. 1,400 parts per billion. That actually, if that were indoor air, that would just about violate the OSHA standards. That's a pretty high level. We did drive by it the next day, and it was, I think it peaked out around 200 parts per billion. So it dissipated, but it was still there. So this is the kind of data we're looking at. And the last slide I'll go show you, and this is one that I got all giggly about Saturday or Sunday night. This was the 1-minute average ammonia that we measured at Camp Williams. So Camp Williams is on the saddle between the 2 valleys here. And the thing I want to point out on this is the concentrations were fairly low, kind of bounced around a little bit. And when they spiked up, the blue and the yellow there, which way was the wind blowing? That's what those black dots show you, wind blowing primarily from the south. The wind data was actually from the Provo airport, so it wasn't at the same site. Some colleagues at the University of Utah did have a very fancy meteorological station there, but I haven't seen their data yet. But it's intriguing that we do see spikes when it comes from the south. So that's pointing to which of these knobs do we turn. We're getting there. That's what my research, what I like to do. So falling back to this is why I do the work I do. I'm not really in it to develop some new air pollution control device. I'm in it to know which knobs that we can turn. How can we best effectively control our air pollution? Utah-wide, other places, I work at other places too. That's what I like to do, and that's what I've been doing. So I'm a little over my time. Not by a lot. We had an interruption. So with that, I will pass the baton on to Alan Max.
Randy, that was great. Really fascinating stuff. And just a plug for research. You know, we've got limited resources in the public sector. And we need to make sure that when we invest those resources, we put it in a place that's going to make a difference. This kind of research that we saw today helps make sure that we are targeting the things that get us the biggest bang for the buck. So that's important. Okay, thanks very much to all of you. Number one, thanks for a good excuse to get away from the legislature for a little while. And number two, thanks for being here and for your concern about air quality. This is a big issue. We all know it. It's on the minds of everybody. I'll just tell you that I've got unambiguous direction from the governor to make it a top priority. And every day, we've got over 100 people in the Division of Air Quality that show up to work passionate. Now, they've got a legal responsibility to get us into compliance, but it goes much beyond that, to a passion to make sure that their families and your families are safe, that our economy can grow and we can all be successful, we can have the best lives possible. So let me just make two quick points. One, the work that's going in is paying off. We're getting better. And number two, we're not there yet. We've got more to do. So on that first point, just a couple of data points. So from 2002 to 2017, 15 years, we've increased our population in the state by 34%. At the same time, we've reduced our overall emissions by 38%. It's essentially, on a per capita basis, cutting our emissions in half. So 2002, every one of us in the state emitted 1 ton of pollution a year. Now it's about half a ton. So that's good. I can also tell you that the Clean Air Act measures compliance on a 3-year rolling average of pollutants. So for particulate matter pollutants, EPA in the last couple of months has certified that we've been in compliance with the Clean Air Act in Cache Valley and in the Provo area. And we're just about to submit some documentation to EPA to get approval for saying that Salt Lake area has been in compliance with the Clean Air Act for the last 3 years. That surprises people. Now, does that mean let's celebrate and walk away victorious? No, that's the first of a long step to be redesignated into attainment. But it's an important milestone showing that when we work together, we make a difference. All right, so let me just talk briefly. We're not there yet. We know that we get bad inversion years, we're right back in it. That there are too many people breathing too many pollutants. So what's the state doing? Can't go through much. I sat down a few months ago and wrote down 5 pages, bullet points, single spaced of the things that are going on. I'm not going to go through all of that. But let me just mention a few things. One of the slides you saw was that there are 3 categories that we generally consider of pollution sources. The first is point sources, or industrial sources. So since about 1995, we've cut our industrial emissions in half. It hasn't been easy. Just at the refineries, for example, about 3% of our overall pollution. They've spent $1 billion in the last 10 years to put controls reduce their emissions, and to provide cleaner fuel. This is not an easy thing, not expensive. Now we're requiring them under a state implementation plan that we just issued to EPA, to put in place best available control technology. So looking at what's going on all over the country and putting in best economically viable technologies. So this is continuing to make progress in the industry. The next area is area sources. As you heard, these are buildings, our homes, wood burning, coatings, paints, small businesses, etc. About 4 years ago, we went and looked at every region in the country, what they were doing. And we took the best strategies anywhere in the country and applied them here. We've currently got the most stringent, most ambitious area source controls in the country, even controlling consumer products. And I gotta tell you, that's had a real impact on my hairsprays, my hair products, but we're working. And the last area is mobile sources, our cars, our trucks. And we can't control that as a state. Those are preempted from state control. So there's been progress in cleaner vehicles, cleaner standards that are coming down. But there are things we can do locally. We've had the most ambitious program to expand mass transit in the country. We've been working on getting some of those dirtiest cars off the road, had some grants that have allowed us to provide incentives to get those gross emitters off the road. But probably the biggest thing we can do is cleaner fuels. Probably heard about Tier 3 fuels. This is the low sulfur that allows our catalytic converters to work better. And when in place, will reduce emissions from all vehicles, the oldest vehicles to today, by more than 10%. And when coupled with Tier 3 vehicles, 2017 model year and beyond, can reduce emissions by 80%. It's 4 of every 5 cars off the road. Here's the problem. We can't require our refineries to produce Tier 3 fuel. We're again preempted by federal law from requiring that. And they can purchase credits from other sources around the country and average out their sulfur content. So what do? And the governor and I went and we twisted some arms at each of the refineries and talked to the executives and said, please step up, do your part. This is important to our community. This is important to your families. And we really appreciate the fact that Chevron, Marathon, Silver Eagle have all committed to produce Tier 3 fuel here. And others are still working on it. The legislature provided some incentives to move that along. So good things happening. There's a lot more we can talk about. Let me just say, there's a passion for improving our air quality. We're working on it. I know you care. I know people in the community care. UCare cares, right, Tom? The public messaging, all of us do our part. So thanks for what you do, and thanks for providing this opportunity.
Thank you, Alan, Randy, and Teresa. And we appreciate all of you taking the time to be with us today. We hope that we have helped you gain an appreciation for the role that Utah State University plays in addressing these critical issues in our state. As I mentioned, Randy isn't our only USU researcher focusing on air quality. And for those of you who had the opportunity, if you didn't, take some time now. At the table out front, we have some flyers depicting some of the research that's being conducted, including understanding characteristics of our erosion-prone climate, determining how dust and snowpack affect our air quality, measuring the health impacts of air pollution, and creating innovative communication initiatives to help change habits. We want to be respectful of your time, so I think Randy is willing to stick around and take some questions here, but for those of you who have their time commitments, we want to respect that and allow you to be free to leave. We also have some refreshments. Also in your folder, you've got some information about future events, and we hope you'll be able to join us and inform your colleagues to do the same on June 18th on water with Dr. Michelle Baker, and on October 1st first on landscape with Dr. Courtney Flint. So we look forward to those presentations as well and sharing that information with you. Also, when you leave, would you please stop by the check-in table in the spirit of the event, recycle your name tag, and we would appreciate your feedback by filling out your survey to allow us to provide an even better presentation for you and more informative in the future. But again, thank you all for being here. Again, our thanks to Dave Peterson, OC Tanner, for making this wonderful space available.